Now we will see how we can use the design equations to actually produce a cavity design. And as with many complex design processes, it requires an iterative numerical approach, and we can accomplish this probably most easily by using a standard Excel spreadsheet approach. Again, a classic engineering design approach. We need to, first of all, set the initial conditions of the design, and we'll go through those now. And the first one, fairly obviously, is the input frequency F0. Now, essentially, this will depend on the application that the thruster is going to be used for. I mean, will it be used for a small CubeSat or a very large launch vehicle? And the application will determine the size of the thruster and the power at which it will operate. So typically for an in-space, low-power, small thruster used on satellites, typically operate around 4 gigahertz. Now, the actual frequency that you use on the satellite will depend on regulatory restraints and more likely the EMC considerations of the satellite itself. You mustn't use a frequency that's going to interfere with the comms and the electronics on the satellite itself, because however good you make the isolation of the cavity, that there will be leakage. If we look at the larger, the high power superconducting thrusters, they're bigger, they're higher power, so the thruster itself will operate at lower frequencies, and typically this can go below 1 gigahertz. Now, although we determine an initial input frequency to the design process, the final value for F0 will actually be determined by the design process itself. We also need to decide on the transmission mode, either TE or TM modes, and we will select the mode mainly depending on the input circuit configuration, whether we're using a slot or a probe or a loop. We need to take into account any size constraints, but we will always try to maximize the Q. All the design processes that we follow aim to maximize the Q because that maximizes the specific thrust that we're aiming for. The actual geometry of the cavity itself will really depend on the type of thruster we're aiming for, but inevitably we will use a circular geometry because it's easier to machine, and really the only rectangular type of cavities would be where we are using flat plates, IPCO thin film substrates. These can be commercially bought in flat substrates. Producing curved thin film IPCO materials is a very specialized process. The maximum diameter, this is the internal diameter D2, is essentially determined by the frequency and the size constraints within the satellite or the vehicle that are applied. The minimum diameter, D2, essentially will be determined by the machining tolerances and the thermal range over which you're going to operate the thruster itself. We'll attempt to approach the cutoff diameter at the operating frequency, but there will always have to be a margin to, as I say, allow for tolerances and thermal specifications. The axial length essentially is determined by size constraints, as always, but we will also have to look at the number of half wavelengths we use to determine resonance. And this, again, will depend on, to a certain extent, on the application of the thruster itself. The so-called first generation thrusters, essentially we'll tend to extend the axial length within the size constraints to maximize the volume of the thruster itself, to maximize the Q and hence the specific thrust. However, if you're looking at superconducting thrusters, particularly the very high Q thrusters for what we term generation 4 thrusters, you will actually try and reduce the axial length, bring the number of half wavelengths down to a single half wavelength, because this minimizes the Doppler shift that we will see much later in these lectures as being a very important factor that you need to take into account for these types of thruster designs. I thought that the best way of illustrating this design process is to use an actual design, and we chose the SPR flight thruster as this example. It's been manufactured and extensively tested because it was actually used as the engineering model for a flight project. So we know an awful lot about this design. The operating frequency was had to be selected between 3,850 megs and 3,900 megs, basically to allow it to be integrated within a satellite payload without interfering with all the other payload frequencies. So it was actually designed for a particular application. We selected the frequency in the middle of that range, so it's 3,875 megahertz was our initial design input. The final design ended up at 3,873.6 megahertz, so it's pretty close to the input requirements. And this gave a lambda naught free space wavelength of 77.37 millimeters. The actual final frequency, as I've said before, is obtained by variation during the design process, and we vary that input frequency whilst monitoring the integrated effective wavelength over the cavity axial length until it equaled 1.5, in fact 3 half wavelengths. Note that the calculation is based on the value of C in air, which you can see quoted there, but because it's clearly going to be used in vacuum, we have to note that the value of C in vacuum is actually different. It is actually 2.99792458 times 10 to the 8th. So you can see it's sort of slightly different to the value of C in air, but you have to go down to 4 decimal places before you see the difference. A TE013 operating mode was chosen. So the p-value is 3, which is 3 half wavelengths, and the operating mode was actually chosen in this case to maximize the cavity volume within the payload dimensional constraints. Circular geometry was chosen, again for ease of machining, and we specified the tolerance for the internal dimensions of plus or minus 0.05 millimeters, plus or minus 50 microns. It's interesting to note that the experimental projects that I've been given information about for all sorts of different research groups, their tolerances have really been sort of, if they're specified at all, they're specified in terms of a couple of millimeters. It's absolutely hopeless trying to manufacture a proper EmDrive cavity unless you're going to apply these tight manufacturing tolerances, and we've talked about the reason for this in the previous lecture. Cavity material was the standard aluminium alloy used in space equipment, and this enabled the space qualification process to take place. Internal surfaces were highly polished and silver plated, again to space specifications. The large end plate internal diameter of 200 millimeters was our starting point. Again, payload dimensional constraints meant that we were held to this sort of maximum value, and it gave a lambda G1 of 87.75 millimeters. So you can see that it's not as low as the lambda 0 of 77.37 millimeters, but we're trying to bring it down, the wavelength down to as close to the free space wavelength as we can within the size constraints, essentially so that the design factor DF is maximized. Small end plate ended up as a diameter of 97 millimeters, giving a lambda G2 of 331.61 millimeters. So you can see the difference between lambda G1 and lambda G2, which, as we've seen before, determines the value, value of design factor, and therefore affects the maximum thrust that we can get out of this device. It's worth noting that the cutoff diameter is 94.36 millimeters, so the difference between the internal diameter of the small end plate of 97 millimeters and cutoff diameter allows quite a reasonable margin for tolerances, and particularly for the large temperature range over which the thruster is operated. The axial length for resonance at the operating frequency of 3,873.6 megahertz was 161.3 millimeters, and this actually gave a taper of 0.638562 millimeters diameter per millimeters length. And throughout this particular slide, you'll see that I'm using high numbers of decimal places for all the parameters that I'm talking about. And this simply reflects the fact that the design process itself also has to have quite high tolerances, as well as the machining of the cavity itself. So now we'll look at the detail of the actual spreadsheet that we use for this design. So we've said that what the initial parameters are for frequency, diameters and length, and we'll apply it in the spreadsheet that we've shown on the slide for the first 5 rows of calculation. We look at the column parameters. Column A is essentially the input to the spreadsheet, and it is the axial length as we work down from the large end plate, and this is incremented at each row by 0.1 millimeters. So if you like, this sets the initial tolerance for the design calculation itself. The internal diameter at the particular axial length that we're inputting in column A is calculated in column B, and this is simply calculated from the taper, where the taper is D1 minus D2 divided by the axial length. So we're calculating the diameter at the particular axial length of the cavity. Now from this we can calculate the guide wavelength, lambda g, from the equation that we've already been introduced to before. And column D is the effective wavelength, which is calculated from the length increment divided by the guide wavelength at that particular axial length. So that's 0.1 divided by lambda g. And we then integrate this effective wavelength over the previous rows to give what we term the total effective wavelength, lambda e. And this effectively is the effective guide wavelength at n, so dn, plus the next one along, which is d of n plus 1. So we're integrating the effective wavelength as we work our way down the axial length of the cavity. And the final column in this first part of the design spreadsheet is the wave impedance, which we're calculating as it changes as we work our way down through the axial length of the cavity. We now extend the spreadsheet for a total of 1,615 rows of calculation. And what we've done, what I've shown here, is the last 5 rows of that particular extension. And what we're doing here is we're extending the axial length of the cavity until the diameter shown in column B starts to approach cutoff diameter. And long before we get there, actually, we are looking in column E, which is the total effective wavelength, until we see it getting as close to 1.5 as the resolution of this particular spreadsheet allows us to get to. At this point, we identify this cell, which is actually where the input length is 161 1.3 millimeters, and the total effective wavelength is as close to 1.5 as we can get. And at this point, we iterate the design by slightly varying the input frequency until we get the value in this particular cell that's illustrated in red to be as close as we can to 1.5. So clearly this will be dependent on the tolerance of the whole spreadsheet itself, but we aim to get as close to 1.5 as we can, and in this case we've got to 1.500 or 149. And this effectively is determining the resonance of the cavity and at what frequency this will operate at. This will in fact resonate at. Now, what is particularly interesting to do is to now extend the spreadsheet until the diameter in column B actually goes below the cutoff diameter. And what I've shown here is the 5 rows around the cutoff. And what you can see is that columns C through to F, which are the ones which are subject to calculation, are no longer able to give a result. This is quite important because it shows that the spreadsheet itself is actually modeling a real microwave condition within the cavity. This isn't just doing a few sums. This is actually modeling correctly what's happening to the electromagnetic wave inside the cavity. And you can see that at a length of 165.5 millimeters, the diameter actually is going below the cutoff diameter, which is 94.36 millimeters. It goes down to 94.32 millimeters, and the rest of the columns just cannot be calculated. It's interesting to note that in the early days of trying to design these resonant tapered cavities, a number of academic institutes immediately went to the easy way of doing it, if you like, which is to just apply finite element analysis, which is available in commercial software packages which all the universities buy for their researchers to use. And what was found, actually, surprisingly enough, was that these early software packages failed because they carried on calculating past the cutoff point, which is clearly not correct. I mean, at cutoff, everything stops. The lambda g goes to infinity, the velocity goes to 0, and therefore whatever these finite element packages were given was absolute nonsense. They were actually described as Mickey Mouse solutions to this difficult calculation process, because they gave jolly nice pictures of what was going on. I mean, the outputs of these commercial packages are very, very colourful. So good pictures, but not real life. They did not actually represent what was actually happening. And in fact, a Chinese university sorted this out It took them 18 months to deconstruct a particular commercial software package and actually apply the correct equations into the software, into the coding, which had not been used previously. I believe that these commercial packages, well, at least some of them, have now been modified to help the academics in their efforts to produce a proper EmDrive design. But you must take any design below cutoff to verify that the technique that you're using is correct, because at that point all calculations should collapse. To help visualize the design process, we now extend the spreadsheet by a further 8 columns. And what we're doing here is plotting the E field and looking at where we want to position the detector probe and the vent hole for the cavity itself. You start off by the input conditions of close to 0 E field at both end plates, simply reflecting the fact that each end plate has a resistance as close to 0 as we can make it. So we calculate the E field itself in column A by providing a sinusoidal function of the effective wavelength. So that's E in this case equals plus or minus d/2 sine 2 pi lambda E. And plotting this gives us just a visual plot of the E field. The tapered walls we've plotted simply by plotting a value plus or minus d1/2, 2 plus or minus d2/2. So that gives you the tapers, and the position of the detector probe is shown by the vertical purple line, and we put this at an E field maximum so that we can have the smallest detector probe as possible, so that we don't load the cavity through the detector probe, but at least we get a good signal from it for the telemetry of the power within the cavity itself. One important point to note is that if we're going to fly this equipment, it has to have a vent hole. All space equipment has to be vented, because as you go up through the atmosphere into vacuum of space, everything outgasses, and you must clear the cavity itself of any residual atmospheric gas. It is actually very important to do this, otherwise you will get breakdown within the cavity itself if you apply significant power. I won't go into the details of it, but this is a known problem with high power fields in equipment that's taken through from the atmosphere at Earth's surface through to the vacuum of space. You must avoid whatever you can a partial vacuum condition inside anything that has very high E fields. Otherwise you get breakdown. And it tends to upset the performance of these pieces of equipment, and indeed has on a number of occasions caused failure of flight equipment. So what we do is we put the vent hole as close to an E field minimum as possible, simply to minimize the EMC effects. We're trying to minimize the leakage at the operating frequency of the cavity itself. So we've shown the further 8 columns in the illustration on the slide. We're looking at the length, which goes in at as a, if you like, as the input to this particular section of the spreadsheet. We're looking at the plus and or minus E fields, or the illustration of the plus or minus E fields, the 2 tapers, and the positions of the detector probe and the vent hole. And really just to complete the overall picture, because this is the visual output, if you like, of the spreadsheet itself, we need to plot the end plates as vertical lines. If you look at the resulting plot given on to the right of the slide, you can see that the E field itself is effectively a sinusoidal function with an extended or an extending base. As you approach the small end plate, you can see the wavelength gradually increasing, and the E field starting to level out as it approaches the small end plate. So now we look at a further extension of this rather large spreadsheet by basically putting in a further 7 columns so that we can produce a visualization of the H field within the cavity. So in this resonant cavity operating in a D01 mode, the E and H fields are not only orthogonal in space, which we've talked about before, but they are also 90 degrees out of phase. So if you like, at each end plate, the initial conditions are a maximum value for the H field, and we do this as we did with the E field by inputting the length in column S and plotting the H fields in columns T and U, or calculating the H fields in columns T and U by using a cosine function. So in this case, H equals plus or minus D over 2 cos 2 pi lambda E. And what you can see is that we are using D as the maximum value of this taper illustration. It's useful to do this to visualize the H field so that we can decide where to position the input loop within the cavity, and this is shown by the dashed red line. And what we do is to attempt to position this particular input loop as close to the H field maximum as we can. It helps the internal matching of the H field between the loop itself and the wave impedance of the cavity at this point of input loop position. We now see how, with the addition of a further 3 columns, we can calculate the guide wavelength and wave impedance as we go down the axial length of the cavity itself. And the important thing to do is to get a feel for these two very important parameters, guide wavelength and wave impedance, as the input conditions to the rows of the spreadsheet itself vary. You can see that if you look at the guide wavelength shown in red, as you approach the small end plate diameter, the guide wavelength rapidly starts to approach infinity. And at the same time, the wave impedance, which is shown as blue, starts to rapidly approach zero. And it is all part of any engineering design, if you can, to get a feel for how parameters change as you vary the input conditions. You can see with anything approaching cutoff conditions within a resonant cavity, things change very rapidly indeed. And you need to understand this to get a feel for the design of the cavity that you are producing. So, as I'm sure you've all noticed, the spreadsheet calculation that we've been talking about makes a rather significant assumption that the two end plates are flat. This is simply to make the calculation simple and possible using just a spreadsheet. Now, we've already said that the one thing that you cannot have is flat end plates, because this means that the length of the wall it becomes larger than the length at the mid position of the cavity, simply by looking at the simple geometry of a flat end plate tapered cavity. So what we need to do to prevent the wavefront distortion that we would otherwise get is to take the length L that we've used in the spreadsheet, and at the annular section of the large end plate, we need to then rotate it up as a radius RA until we meet the actual tapered wall. This actually means that the real value of D1 is actually slightly less than the value that we put into the spreadsheet itself. It does create a small error in the result, but not a particularly significant one. So when you go from the spreadsheet design to starting to draw up the cavity itself on your engineering drawings, then clearly you have to take this curvature of the annular section of the large end plate into account and maintain the radius RA. So the acid test of any engineering design is, do you get the results that you expected when you actually manufacture and test the device? And what we've done here is to take the initial design parameters, the main initial design parameters, and compare them to what we measured over a quite extensive test period for this particular flight thruster. And the first thing that we look at is the operating frequency. And you can remember that we said the design frequency at the end of the optimization process using the spreadsheet was in fact 3,873.6 megahertz. When we carefully tuned and tested the cavity, we arrived at a resonant frequency of 3,850.7 megahertz. So this is about 0.6% error. And if you go back to the previous slide, you can see that we did expect an error due to the design calculation assuming flat end plates. But also, quite interestingly, when we did some very careful internal plots of the fields within the cavity, we found that there was a small amount of field distortion around the input loop. And this also actually contributes to the difference between the test frequency and the design frequency. And we have actually noticed that this is consistent with a pretty consistent error rate across a number of cavity designs. The other critical parameter for the EmDrive cavity is the Q that you end up with, because we keep emphasizing that the higher the Q, the higher the specific thrust you get. And we started off with a maximum theoretical Q of 73,243. Now, we did a lot of careful measurements of Q by essentially doing a swept frequency measurement across the input of the cavity and taking the 3 dB bandwidth to calculate the unloaded Q of the cavity. If you remember, the unloaded Q of the cavity for an optimized design is actually twice the what you measured as the loaded Q, because in this situation the Q of the input circuit is the same as the unloaded Q of the cavity. The result of this is that when you measured the unloaded Q of the cavity, it's going to be significantly less than the maximum theoretical Q, simply because of the tolerance of the machining itself, of the tolerance of the alignment of the end plates. And we went through this before, and in the previous lecture we actually gave a plot of the variation of unloaded Q against the tolerances that we applied. So it was not unexpected that we got this 24.7% reduction in the actual Q from the theoretical Q. Interestingly, when we made our first superconducting cavity, we got a measured Q higher than the design value. Very happy about this, of course, but wondered why this should be the case, as we expected to get a similar reduction in measured Q to theoretical Q. And we talked to the suppliers of the thin film superconducting material and found in true German engineering tradition, they would have been very conservative with their specified values of surface resistance. So we gained quite a bit from this particular supplier in this way. The measured specific thrust, which you see from the table, was slightly higher than the design specific thrust. We got 326 millinewtons per kilowatt as against 301 millinewtons per kilowatt for the theoretical value. And this 8% difference, we believe was due to the measured Q that we were using to calculate the specific thrust, for the theoretical design specific thrust. This Q that we measured was actually lower than the real unloaded Q of the cavity, because we were including within our measurement, which was done at the input of the cavity, we were unable to take into account the loading effect of the detector probe. You'll remember during the earlier part of this lecture, we said we make the loading of the detector probe as low as possible, and it looks like in this case the detector probe was loading the measured value of Q by about 8%. The final row in the table that we give here, comparing test results to the design results, is particularly interesting because we compare the end plate temperature ratio. So we actually measured the end plate temperatures over a significant number of tests. We actually used the, if you like, the buy-off tests of 19 performance measurements from 130 watts to 455 watts. We took these measured temperatures and ended up with a mean test value of 0.69 as a ratio between the two end plate temperatures. So we now compare this with what we get from the design of the cavity. And here we go back to the very basic theory behind EmDrive, which is that the two forces at the end plates are different. They will therefore give rise to different power losses. So we expect to get a much larger power loss at the large end plate than at the small end plate, because the forces at the large end plate are much higher than the forces at the small end plate. We need to take into account that the dissipation area of these two plates is different. And from that, we can calculate what should be the theoretical end plate temperature ratio, which comes out remarkably close to the test measurements. We got 0.66 as a ratio from theoretical considerations to 0.69 from what we got on test. And this was considered not only by us, but also by the people that, if you like, were buying this design from us, as being a very significant verification of the basic theory behind EmDrive operation. And we were very pleased to get this particular result. So now it's over to you guys to start doing your own designs and start doing some work yourselves. What I suggest you do is, as a first design exercise, take the design model for the SPR limited flight thruster that we've gone through in quite excruciating detail up to now. Take those initial parameters, which I've reproduced here in paragraph 1 of this slide, and run the design model in TE013 mode until you get the results that are compatible with what the actual results were that we've already discussed. Now, having confirmed to yourself that you have indeed now produced your own Excel design model. What I suggest you do is do indeed what we have to do and run the design model for different modes. And this is important. A modal analysis is important for any practical design to make sure that you don't inadvertently end up with resonant frequencies for different modes that are too close to the design frequency that you're going for. And I would suggest that you run your design model for TE11, TE21, TM01 and TM11 modes, and just see what resonant frequencies you come up with. And you can then decide yourself whether these are going to cause you problems or not. Now, to help with this, I've given you the values of KNM for the TM modes, much as you had the values for the TE modes in a previous lecture. So run those for different modes. What you will end up is, as I say, a set of frequency differences. And just to give you a feeling for what you're trying to aim for, I've given you a set of results for a mode analysis of a different thruster. I'm not going to enable you to cheat too easily. Now, these are the results for a 2.45 gigahertz thruster operating in T012 mode. And you can see for the various modes, the frequency differences are quite acceptable to the nominal design frequency. So there's no real chance of any overlapping spurious modes for this particular design, and that's what you must aim for in all your designs. As a final set of interesting data, I suggest you run your design model for different temperatures. So you need to calculate the dimensions at the two extremes, for instance, of the qualification temperature range, minus 40 degrees C being the low end and plus 90 degrees C being the top end. Run the design model and make sure that the system will still work under these extremes of temperatures. For information, what we used for the design model initial conditions, we assumed a temperature of plus 20 degrees C. So that gives you plenty of work to do with hopefully enough information to enable you to compare your own results with what they should be and correct any problems you may have with your own design spreadsheets. Once you're happy that you have a working design model, what I suggest you do is then look at the sort of thrusters that we are going to be looking at in later lectures for different applications. One that immediately springs to mind is for a thruster for a CubeSat operating at 3.85 gigahertz in a TE113 mode and start with a diameter D1 of 150 millimeters. The reason why I suggest this is that I would think that this is probably the first practical design, flight design, that you may actually be able to sell to other people. It's a straightforward first generation thruster design with wide applications in small CubeSats. Another design that we'll be looking at in future um, lectures will be for an unmanned airborne vehicle, and this will be a superconducting thruster, a so-called second generation thruster, operating in at a frequency of 2.45 gigahertz, and it's operating in a TE211 mode. Sorry, I couldn't actually see that because of the window in this particular slide. So this will be for possibly the first vehicle that you might fly in a subsequent development program, which again we will talk about in future lectures. Finally, I suggest a design for a very large thruster, which we will talk about for instance, a deep space probe. This is a what we term a generation 4 type thruster. It will be operating in T211 mode at a low frequency, 0.95 gigahertz, and with a significantly large diameter, D1 equal to 500 millimeters. This will set you up very well for looking at how these applications are used, what these vehicles will actually do in later lectures of this series.